So today is our great pleasure to have Nikita give a seminar. So he got a bachelor from Duke back in 2019 in physics and computer science. Then he went for 1 year to work for Google. And then he came back to academia and joined here at UW as a grad student. And today he's going to talk about his recent work on detecting particle production on quantum computer. Please, Nikita.
Thanks, Mark, for the introduction. Yeah, my name is Nikita. I'm a graduate student in InQubator, and today I'm going to tell you all about our recent work that came out on the archive last week, where we saw evidence for particle production in quantum simulations of scattering. So the motivation for this work comes from looking at collisions that happen at high energies, for example, in the LHC or other similar colliders. And so here I have a cartoon of what these collisions look like. You start out with two wave packets of particles that are traveling at very high speeds, traveling towards each other. They move towards each other, collide, and then some post-collision state forms. And kind of the goal of all these simulations and of these colliders is to study the dynamics of these collisions and what happens, what forms after the collision takes place. And so studying these dynamics directly from the quantum field theory degrees of freedom that describe these processes is considered to be, believed to be classically challenging. But we believe that with quantum computers, we can do this directly from the QFT degrees of freedom. And so this is in this talk, I'm gonna explain how we set up these simulations on quantum computers. So here I'm showing several of the quantum simulations of scattering that have been done to date before this work. One on the Turing model and one on the scalar field theory. And so these are just two examples, but the main thing about these early scattering simulations is that they have been limited to low energies and to small wave packet sizes. And both of those limitations come from device capabilities, but also from algorithmic capabilities. But if we and as a result of that, all the scattering simulations that have been done to date have been focused on low energy, so elastic collisions where there are no additional particles produced. And if we really want to look at some high energy process where there are more interesting post-collision states, we want to increase the energy, but also this means increase the size of the wave packet so that we can really target some inelastic channel in these collisions. And so on the other hand, there have been classical simulations of these inelastic processes that have been done in one dimension using matrix product states. And so this is a classical simulation technique that is very efficient in one dimension. And so here I'm showing two more examples, one in the Ising field theory and one in the U1 theory. And so the way, so what is going on in these simulations is that you start with two particles on the bottom of these plots. These are these bright spots. And you start with two particles that are traveling towards each other, and they collide in the middle. And then after that, there is some state that forms that might have interesting properties. And so as you read these plots from left to right, you can see that as you increase the energy of the collision process, the dynamics of the process really changes. So for example, in the middle of these plots, you can see that there is some bound state forming or resonance forming. And then on the right plots, you can see that there's some new particles being produced in these extra set of tracks. And so the nice thing about these kind of simulations is that they're very visual, and you can really see when there are new states forming in these collisions, when there are new particles being produced. And so this is kind of a nice motivation to actually do this in a quantum simulation where you might be able to exceed the capabilities of classical computing, like I've shown here. Okay, so an outline for the rest of the talk. First, I will describe this new wave packet preparation algorithm that we have developed in this work that really enables us to scale up the size of our wave packets in a systematic way. it enables us to prepare them and do these simulations on devices that are available today, quantum devices that are available today. And then I'll show some results of the quantum simulations that we did with this wave packet preparation algorithm, where we actually see inelastic effects on particle production. And so this paper came out last week on the archive, and you can find it here. If you're interested, you can look more information there. So a quantum simulation of scattering starts with by preparing particles, wave packets. And there have been many algorithms that have been targeting these kind of wave packet preparation procedures to date. The main problem with most of them is that they require a circuit depth that scales with the wave packet volume, or at least linearly with the wave packet volume, or even higher than that. And that kind of, while this is efficient formally, it's only polynomial in the wave packet volume or the system size. While this is efficient formally, this kind of precludes any demonstrations in the near term, just because of the circuit depth that is required to have a large wave packet. And other methods that don't encounter this problem, they usually come with an exponential classical computing overhead. And so these both are kind of prohibitive. But the algorithm that we introduce, it requires constant depth, and so this really enables us to do these things on devices that are available today. And so the algorithm that I'm going to present in the several slides, we have tested it in several theories, in the 1- and 2-dimensional Ising field theories, in the scalar field theory, and also in the Schwinger model. So I want to emphasize that this method is applicable to a range of theories. But for concreteness, I'll just focus on the 1-dimensional Ising theory, because there it's really easy to write down and explain how this algorithm works. So the Ising field theory has this familiar Hamiltonian, has ZZ interaction between neighboring sites, and transverse field X, and a longitudinal field Z. And it turns out that this Hamiltonian has a field theory limit if you take the coefficient of the transverse field to 1 and the coefficient of the longitudinal field, the GZ, to 0, but you hold this ratio that I've written here fixed. And in general, if you had GZ equals 0 from the start, this would map onto Majorana fermions, which is a integrable model that might be familiar to people. But for arbitrary values of the longitudinal field, this maps onto general non-integrable theory that has very interesting dynamics that are hard to simulate using classical methods. And so one thing I want to point out is that this model has a symmetry under spatial translation. So if you pick up the Hamiltonian and translate it by one site, it looks the same. And this is going to be important for the algorithm that we use to prepare wave packets. So the structure of the Hamiltonian, like I was saying, if this Hamiltonian has translational invariance, it decomposes into a block diagonal structure where each block is labeled by momentum k. And within each block, so within the momentum 0 block, the lowest energy of that block, the lowest energy state of that block is the vacuum. And the higher energy states of that block are, the first excited state of that block is the single particle at rest. And the ground states of other blocks are single particle states with momentum k. And so this is kind of what I've drawn here. And what we're really after is creating wave packets, and wave packets are these Gaussian superpositions of these single particle eigenstates. And so in the next slides, I'll show you how using these single particle eigenstates, we can build out these Gaussian wave packets. So first, let's start with one way to prepare these single particle eigenstates psi k. So one way to do this is by preparing some state that is inside of the given momentum block that you're interested in, hk, as I've written here. One simple state is just the state with that has the bit string of all zeros and just a single one, and all other bit strings that are related to that state by translation. And then if you add the appropriate phase, such that when you pick up the state and translate it by one site, you get the phase back that you would expect from a state with momentum k. This is what I'm calling the state at k. So prepare this state in some way on your quantum device, and that gives you a state that is in the correct momentum block, but it might have contributions from high energy states or high energy states such as states with more particles or states with heavier single particles. And so once you prepare that state, then you can minimize this energy. And if you use translationally invariant circuits, then this guarantees that it's not going to take the state into any other momentum block. So it's going to respect the momentum structure of the state. And what I mean by translationally invariant is that if you pick up a circuit and move it down by one site on your qubits, then the circuit stays the same. And so using this method, because we know that our wave packets are just linear superpositions of these single particle eigenstates psi k, we can use a very similar method to prepare the wave packets that we're after. So to prepare wave packets, you start with a different state. Now I'm calling this W of k, which is just a superposition, a Gaussian superposition of these states k that I was showing on the previous slide. And then again, you use translation invariant circuits to minimize the energy and create a single particle wave packet. And at this step, there's an additional requirement that these circuits must be real. And so one nice thing to note about this W state is that in general, it has these arbitrary complex coefficients that specify the position and momentum of the particle you're creating. But if you set all of these coefficients to be equal, this actually gives a W state that is well studied in quantum information science for its properties and applications to cryptography and things like that. And so people have thought long and hard about how to prepare these states efficiently on quantum computers. And we can take advantage of these developments to prepare the W of k state that we want as the initialization for our wave packets. And so we use these techniques from these three papers to prepare this W of k state, which is a generalization of the W state that people normally work with. And we prepare it in a fixed depth of 7. And here I have a cartoon of how this circuit works. And I'm not going to go into the details, but the main important things about it are that this circuit uses measurement and feed forward to prepare this in a fixed depth. And by doing that, you can really spread correlations throughout your wave packet using classical communication. And that allows us to prepare these wave packets in a depth that does not scale with their size. And so here I'm just going to show what all steps of this wave packet preparation look like. So you have, yes, first you start with this W of k state that specifies the momentum content of your wave packet. And then you apply these energy minimization circuits that don't change the momentum content because they are aware of the symmetries that your system has. And here I have these pictures that show that in the beginning you have a state with many particles or also heavy particles, and then as you apply this energy minimization scheme, you really get a state with a single particle, and that is the wave packet that you're after. And so here I'm showing some results of executing this algorithm on state vector simulator on a system size of 28 qubits. And on the left, I'm showing so as you apply this energy minimization scheme as a function of the depth of your circuit, that the energy is really reduced. And you can see for various choices of the couplings in the Hamiltonian that the energy really does go down. And on the right, I'm showing the overlap with the exact wave packet that you can find from exact diagonalization. So because this is a small system, you can do that. And you can you can just directly compute what is the infidelity with the state I actually want to prepare versus the one I get from this variational method. And you can see that by minimizing the energy, which is the plot on the right, on the left, the quality of the state that I prepare is also increased. And this is what I'm showing on the plot on the right. But in general, we don't want to just work with small systems. We want to work with very large systems. So here I'm showing a plot of doing this algorithm on 256 site lattice. And for such large lattices, you no longer have access to the exact solution, so you can't compute the infidelity or things like that, but instead you can compare the energy density. So here I'm showing the energy density between the wave packets at size 28 and size 256. So lattice size 228 and 256 with the size of the wave packet fixed. And you can see that because the energy density is the same or very close, this is kind of like extra confirmation that yeah, the quality is comparable for a wave packet on a large lattice and on a small lattice. And so we can do these large wave packet preparation using matrix product state simulation techniques, and this is efficient in one dimension. And so this is what we were able to do in 1D. So now I'm going to shift the gear a little bit and talk about how we use this algorithm to actually prepare wave packets and run scattering simulations on a quantum computer. So here I'm showing the Hamiltonian again, and this is just to say that with the couplings that we work with, we have two stable particles, and I'm labeling the lowest energy, so the lightest particle as this blue ball and the heavier particle as this red ball, and I'll use these colors in the for the rest of the talk. So that's what they're going to mean. And what I mean when I say stable particles is that there is no kinematically allowed process that allows particles to decay into any other particles. So that's what I mean by stable. So here I'm showing the results of using our algorithm with matrix product state simulators to simulate some scattering process. And what I'm showing here is that as you increase the energy from left to right, you can see that some qualitatively different behavior happens. So here I've labeled the total energy of the collision process divided by the threshold energy. And the threshold energy just means that when you're at this threshold energy, the kinematics of the process allow you to produce or convert one of the initial particles to a different one. So here what I'm doing is that I'm starting with two blue particles and I'm increasing their initial speed. And if I increase it beyond the threshold energy, if I increase the speed such that the initial energy is beyond the threshold energy, you can see that there is some probability for converting one of these blue particles to a red particle. And the way to see that from these plots is that because the produced red particle is heavier than the blue one, it's going to travel slower. And that's why these new tracks that are coming in on the right plot are closer to the center of the collision. This just means that the red particles are traveling slower. And so that's how, by looking at these plots, you can really distinguish what particles where. And so I'm gonna use these labels to label and distinguish the elastic case, which is on the left, from the inelastic case, which is on the right. So here I just wanna point out that even though these pictures, for example, this picture on the right has 4 sets of tracks or paths, there's no component of the wave function after the collision happens that has 4 particles. And instead, it's just the superposition of 2 blue particles, 1 blue, 1 red, and 1 red, 1 blue. And but because you do this measurement of the superposition, you see all 4 tracks, but in reality, there's only ever 2 particles in these simulations. So now I'm just going to discuss a little bit about how we choose the parameters for these simulations. So here I'm showing how we choose the energy of our collision. So overall, the goal of our simulations is to see the clearest signal from the quantum computer of this particle production. And we want to find the regime where the resulting tracks of the second heavier particle are separated as far as possible from the elastic tracks. And so we can do that by looking at the dispersion relation. So this is what I've plotted on the left. And we're getting this from exact diagonalization calculations. And we are sure that these are converged at the system size that we use for the parameters that we're working with. And so in the middle plot, I'm showing the group velocity, so the velocity that particles will travel with for a given momentum. And on the right, I'm showing for this inelastic process, where I convert one of the blue particles to a red particle, what is the resulting velocity of the outgoing particles after the collision. And I have highlighted this band in blue, which kind of shows that at the middle of this band, this is where at this momentum, the outgoing particles, the red outgoing particles, which are given by these beige yellow dots, are separated from the speed of the outgoing red particles is much slower than the speed of the outgoing blue particles, and that's given by the separation between the blue and the beige lines. So this is the momentum that we want to work with, and that's how we chose it. And here I'm showing what are the effects of Trotter errors. So as in any quantum simulation, we have to do time evolution by Trotterization, and it's important to consider what effect the Trotter step size has on your simulation. And so I've plotted here a range of Trotter step sizes and also the exact solution for a small system. And so on the plots on the left, you can see that as you increase the Trotter step size, you are really heated to the chaotic regime. And this is given by this line in the red. And there, the dynamics don't really resemble the dynamics of the original system that you're simulating. So we definitely don't want to use a Trotter step that's that large, but maybe we can use one of these orange ones in the middle. And so next we can look at what the actual dynamics look like as with these different Trotter step sizes, and this is what is given in the 4 plots on the right. So in the middle column, I have time equals 25, and on the right, I have time equals 35. These are just two times after the particles have already collided. And you can see that on the top row, the main feature is that the larger your Trotter step is, the slower the particles travel. And this is because the dispersion relation and the group velocity is modified because of the Trotterized Hamiltonian that you're evolving with. So we can adjust this, and this is so we can adjust the positions of these peaks so that the peaks align. And so it's like an apples to apples comparison of what does the post-collision state look like. And so you can that is what is plotted on the bottom row. And you can see that as you increase the Trotter step size, the inelastic effects are really washed out. And so it's important to pick a Trotter step size that still shows the effects that you want to see, but is as large as possible to minimize your circuit depth, so you can go as far as in time as you can. And so this informs our choice, and we choose this light blue line, which is the Trotter step size of 1/2. And so here I'm showing how we chose the wave packet size. And so the top row is the inelastic process, where 2 blue particles become 1 red, 1 blue. And the bottom row is the elastic process. And from left to right, I'm decreasing the size of the wave packet and looking at what happens. So on the left, on the top row on the left, you can clearly see that there is the second set of tracks, which is the new red particle that is produced. And as you decrease the initial size of the wave packets, you can see that these inelastic effects, this second set of tracks, just completely disappears. And instead, you get this interference pattern from a wider range of momentum. And the reason this happens is that as you decrease the size of your wave packet, the size in momentum space increases. And because the dispersion relation is not flat, so because the group velocity is changing as a function of momentum, different momenta are traveling with different components of different momentum are traveling with different speeds. And as a result, you get these spreading and interference effects. And so it's important to choose a wave packet size that actually that shows what you want to see. But you want to choose one that is not very large. And so because of that, we choose 22. And so considering the bottom row also, it's important to be able to distinguish the elastic channel on its own. And you can see that as you decrease the size of the wave packet D, the elastic channel, so the wave packet just spreads a lot more, and you also get these interference effects. And so, yeah, as a result of these two considerations, we choose a D of 22. And so now I'm just going to go through the circuits that we use to do these simulations. So in the first part of the talk, I was describing a constant depth circuit that you could run on a quantum computer that prepares wave packets in a depth that's independent of the size. And we've done that, but it turns out that with the parameters of the device, so how long it takes the device to do these mid-circuit measurements and decide what to do next, the results are just too noisy. So instead, we use this linear depth circuit. So its depth is linear with the system size. We use this linear depth circuit to prepare this initial state W of K that I was talking about before. And as a result of the way the circuit works, it's most optimal for odd size wave packets. So we use a size of equals 21. And this is this step is depth 21. And after applying the circuit, you get this W of K state that I was talking about before. And it has the right momentum, but it can have contributions from high energy states, or that might be heavier single particles or multiple particle states. And then what we do next is we apply this energy minimization step, which really reduces the particle content to 1 in each of these wave packets. So we do this using a method called adapt VQE, which is aware of the symmetries that we have in the model. So it does not change the momentum content of the wave packet, but it really reduces the particle content to 1. And then after that, we have the wave packets that we want with the momentum that we're interested in. And so then we just apply trotterization to evolve our system forward in time. And one thing I want to mention here is that recently IBM came out with these native RZZ gates. So you don't have to compile ZZ interactions into other native gates. And that really helps us cut down on the circuit depth and enables us to go out further in time in our simulations. And so that is quite neat. And so one of the nice things about doing these device runs is that sometimes you see things that you don't expect, and then you have to understand what's going on. And in our case, one of these kind of things that we saw was that initially our results were much more noisy than we expected. So we were comparing to simulations that we had run in the past that were of similar circuit depths, and we were getting much noisier results. And so we realized that because our wave packets are much larger than we had used in the past, they have to travel further to fully overlap and separate after the collision. And as a result of that, the system must be evolved for more for a longer time, and that effectively gives more time for errors to spread and contaminate the results. So here I have a cartoon of two time evolution circuits that are the same depth, but the circuit on the right has a trotter step that is twice as large and evolves the system for twice the amount of time. And what this cartoon is showing is that if you have some error that affects a qubit at the beginning of this time evolution, then with a longer evolution time, this error can spread to more observables at the end once they are measured. And so this really told us that the errors spread with the light cone of the system that you're simulating and not with the device light cone, not with the circuit light cone, as long as the other gates surrounding this error are good. And so this kind of forced us to be really picky about which gates and which qubits we use on the device, more picky than we were in the past. And so to deal with these errors, like any quantum simulation today, we have to do error mitigation. And the main ingredient of our air mitigation strategy is to run a second set of circuits whose answer we know ahead of time, but whose noise is similar to the circuit that we actually are interested in. And so we call this a mitigation circuit. And we use this mitigation circuit to learn about the noise that we have in our physics circuit and then account for the effects of that noise. And in this work, we use the time evolution of the vacuum state as this mitigation circuit. So, and this is easy to compute classically because the vacuum is an eigenstate of the Hamiltonian, and in the absence of device errors and Trotter errors and state preparation errors, this state wouldn't evolve at all, and so it's easy to figure out what the resulting state after this circuit should be. And so we use this state to learn about the noise that we have in our physics circuit, which is the circuit with two wave packets and the actual scattering that we're interested in. And another ingredient that we have in our air mitigation strategy comes from energy conservation. So as a result of Trotter errors and as a result of imperfect air mitigation and other cumulative effects that might build up, energy might not be conserved in the final results that we measure. And one thing that you can do that turns out to help a lot is to reinforce this energy conservation by scaling the results back up to what they were at time equals 0. And this turns out to clean up the results quite a bit. So here I'm showing a plot that has a lot of different data, so I'm going to walk through it. But the panel on the bottom is showing the results before and after the error mitigation. So these diamonds that are kind of in the middle is the raw data that you get from this device, IBM Marrakesh. And the circles with error bars are the values that you get after error mitigation. And so you can see that these diamonds, the raw results, are much closer to the completely decohered results that you would, so the results that you would get if the state was completely random. And that is given by the small dashed line at the top. And you can see that these raw results are much closer to the completely decohered results than to what you actually want. And it's important to notice that there's a line break here. But after applying this error mitigation, you can see that you really recover a lot of the signal that you intend to do, that you intend to simulate. And in the panels at the top, I am highlighting one other thing that we noticed on the device results that we were not expecting, and this is an asymmetry in the noise that we are seeing on the device. So to compute the energy of the system, so what I'm plotting here is the energy of the state as a function of position. And so to compute the energy of the system, we measure the terms of the Hamiltonian, which are z, z, and x. And so we perform two sets of these simulations, one where we measure in the z basis, one where we measure in the x basis. And we see that the results of the z measurements are consistently noisier than the results of the x and the zz measurements. And why this is happening is kind of a mystery to us. On one hand, we don't expect them to be the same because of the way that our error mitigation works, but we would at least expect them to be similar. And so this is something that we are still investigating. So here I'm going to show some of the results from the quantum simulations that we've done on the IBM quantum computer, IBM Marrakesh. So on the left, I'm showing the same matrix product state simulation that I was showing earlier. And I've highlighted 3 simulation times that we have data from the quantum computer for. And so here I'm plotting the energy density as a function of the position on the lattice. And so, yeah, this bottom plot in the middle shows the state directly before the collision. So the wave packets have moved a little bit, but they are not, they have not fully collided and overlapped yet. And then as you go up, so as you increase the time, the wave packets collide and start to separate, and that's what you see in the center plot in the middle and the top plot in the middle. And so as you look at these plots from bottom to top, you can see that the amount of noise in these plots is increasing. So I'm comparing the results from the quantum computer, which are the points with error bars, to matrix plot simulations, which are the dashed lines. And this is kind of what we expect the results from the quantum computer should be. And you see that as the circuits get deeper, as we simulate further and further in time, the results do get a little bit noisier, but it's nice to see that the overall signatures are still there. So this is kind of the limit of the capabilities of the device that we were able to see. But what we really want to see is a stronger signal of these inelastic effects. So here I'm showing this box again, where I'm pointing to one of the tall bumps, which is this blue particle, which kind of dominates the results in the energy density, and then I'm pointing to the bump that corresponds to the red particle, which is much smaller. But if you go out a little bit further in time than we were able to, you can see this bump more distinguished from the data. And so although we can't see that now, if we look at the T3, so T3 equals 25 plot, the second from the top, you can see already some signatures of this inelastic particle production. And the way you can see that is by looking at the region where one of the wave packets is localized. And you can see that it is slightly asymmetric, and the results are skewed closer to the center of the collision. And that is the reason for that is this second set of tracks from the red particle, from the heavier red particle coming in. And yeah, while it would be really nice to go out further, it's already great that we can see some evidence of this particle production from the devices we have today. And yeah, the deepest simulations that we ran took more than 6,000 T-cubic gates with a T-cubic gate depth of 194. So this is really pushing the capabilities of the device that we have. And here on the right, I'm just showing the layout of the gates and the qubits that we used on this IBM Marrakesh device. And the orange points are where the wave packets were located initially at time equals 0. And so just to wrap up and show what we're thinking about next, it's important to remember that this method that we developed is especially advantageous in higher dimensions. And what I mean by that is, if you have a method that scales linearly with the wave packet size, and say you want to create a wave packet that is has support over a 10 by 10 by 10 lattice in 3 dimensions, you would need on the order of 1,000 gates to do that, 1,000 gate depth. But with our method, you can do that in constant depth. And that is really nice because it really enables you to do something in the near term in higher dimensions on the devices that are becoming available today. And so on the right, I have this picture from Google of the device that they recently released, Willow, just a few months ago. And it has this really nice 2-dimensional connectivity. And while you can't do something like a 10 by 10 by 10 wave packet here, you can really start to explore wave packets in higher dimensions than just one. And it's important to have this grid connectivity so that you can have the native connectivity that your model requires. And so this is kind of the simulations that will be enabled by the work that we've developed, but also by the devices that are being released. Yeah, and so with that, I would like to thank you all for listening. The archive link is there, and then it came out last week. If you are interested in more details, please ask me questions now or look on the archive. And I'd like to thank my collaborators, Roland, Mark, and John. And I'd also like to thank IBM for giving us time to run on these devices. And yeah, any questions, I'll be happy to answer them. Thank you.
What can you do to further improve the results before fault tolerance?
You're asking what I can do or what can be done in general?
What can be done in general?
Well, you can make a device that's less noisy.
Sure.
That's one thing you could do, and so that's one thing we're looking forward to. You can improve your error mitigation techniques, so you can have a better way of measuring the noise that you actually have in your simulation, either by coming up with a circuit whose noise is more similar to the circuit you actually care about, or by using some more complicated error mitigation strategies. You could look into like circuit compression techniques that that people have worked on that use, like, for example, variational methods to reduce the circuit depth so that the results are less noisy.
For the real-time part.
For the time evolution part, or yeah.
The state preparation is already optimizing something.
State preparation, yeah. So if we were able to do this mid-circuit measurement method to create in constant depth, that is probably optimal already. We weren't able to do that in this work just because measurement is like an order of magnitude longer than gates, and because of just because of that time you pick up noise during that measurement process. But yeah, in general, you could think about compressing the circuits also. Aranya.
Can you go back to that slide where you saw the asymmetric spreading of errors?
Yes, this one.
Do you think, I don't have form thoughts on this, but do you think understanding why it's asymmetric could help with error mitigation?
Yeah,
So you can preemptively, go ahead, sorry.
Yeah, it would certainly increase the quality of the results. In this case, we are lucky that Z is the measurement that is noisier.
Yeah.
Because the coefficient on Z in our Hamiltonian is small, so it kind of reduces the effects of this noise overall. But if you look at the relative contribution of the noise to the error bars in the results, this Z noise is about half of the error bars. So yes.
That's a lot. Yeah.
Yeah, I mean, we have three terms, so it's not completely out of the out of this world, but it would be great to figure out in general why this kind of asymmetry occurs.
Do you have any nascent ideas on what's driving?
Well, yeah. So this I kind of glossed over this, but so the way we get these data is by doing Pauli twirling, and that converts whatever coherent errors that you have into stochastic errors, and those stochastic errors give you a Pauli channel, which for a Pauli observable that just scales down the value of the observable, and so that is what's plotted. The results of those Pauli twirls are what's plotted on the top right three plots. But when you do Pauli twirling, there's no reason to assume that the weights of each Pauli term should be equal.
Yeah.
But there's also no reason for them to be such a large hierarchy. So we have several ideas. First, maybe the coefficients in our Hamiltonian have an effect on this, because the coefficient on X is 1.25 and the coefficient on Z is 0.15. So there's a hierarchy there. So maybe changing the couplings would do something. The other thing is that on IBM the Z gates are virtual.
Yeah.
So the Z gates essentially have no noise. And so if you just look at the data I'm showing here, if the Z gates have no noise, then Z conjugates X, X conjugates Z. So if Z has no noise, then it's reasonable to expect that X is perfect. But X does have noise because X is physical gate, so that that kind of explains why Z is lower. But it doesn't really make sense that ZZ is also high. So this doesn't really explain the full picture.
Yeah, I was also wondering when you determine those Pauli weights, is there a way to engineer those Pauli weights ahead of time?
Yeah, I'm not sure. There are ways to characterize the noise, like do a full characterization of like a local version of the noise, but we haven't done that. That is one thing that we could do to try to improve this.
Before you do the whole kind of process.
Yeah. You have a question?
For the scaling in higher dimensions, are you anticipating for like the energy minimization is all going to be constant depth, and also for the state preparation?
So the energy minimization is not necessarily constant depth. First of all, it scales with the correlation length. And there's, at least I don't see a way to get around that. So first of all, things are always going to scale with the correlation length of the system. There is also a scaling with, there's like a light scaling with the dimension because you have to trotterize the operators that you apply. And so in one dimension, it's like even odd and then odd even odd on even. In two dimensions, it's like even odd on even, and then in the other axis, even odd on even. So it grows like that. But in general, I don't see why the energy minimization would incur any other growth beyond that.
So I guess one of the big, kind of advantages of this technique is the fact that you can kind of, change the coefficients of these W states and kind of, and so I guess, do you have arbitrary control over those? And I guess if so, can you think about how this technique can be applied to situations like outside of scattering, to give kind of a really nice speed up?
I personally have not thought about the application of this W of K naught state for other, couplings to things outside of scattering. But the techniques that we use and the techniques that we generalize to prepare those W of K naught state were originally developed for the preparation of just plain W states. And those states are used in cryptography and sending signals, like all of these things. So there's definitely applications in that. In general, these mid-circuit measurement techniques are good at, spreading initial entanglement, so spreading like quantum correlations, and then what people do to prepare like an arbitrary long-range entangled state, for example, is to apply like a local variational circuit or some kind of local circuit that you know how to do to just like change the form of that entanglement. So I could see there being some applications in kind of in that direction, but I don't have anything concrete.
Yeah, you use the measurements to kind of put you in the right entanglement phase, and then use the local circuits to kind of move around it.
Yeah, essentially.
Yannick, Sebastian?
Yep, thanks for the nice talk. Could you comment about the choice of GX and GZ? Why did you pick this value 1.25 and 0.15?
Yes, we chose these for several reasons. So we wanted there to be two particles. So we wanted to be in a regime where we can create another particle from these light particles. That's one. And yeah, so if you pick GX and GZ in different ways, you can go from the regime where there are 3 particles to 2 particles to 1 particle, and there in the limiting cases there's like the E8 theory, which has 8 particles, and the definition of particles is different there. That's one reason we wanted a theory with 2 particles, and the other was that we wanted a correlation length that was not very large, and that there's 2 reasons for that. One is because that increases the depth of our energy minimization circuits. So a larger correlation length needs larger deeper energy minimization circuits, but also we would have to increase the size of our wave packets if we had a longer correlation length. So this was kind of like the sweet spot between, even though we're still very far from the continuum, we have the right particle content in our theory and also the correlation length not too large.
So you use the Z basis, is it right?
Sorry?
The computational basis is the Z basis?
Yeah, that's right.
Intuitively, it looked to me like the X basis would be better, but because it's a dominant term in the Hamiltonian.
Better for what?
To have particle states, to have. So you show this wave packet with 0001 and so on and so on. And yeah. So this is in the Z basis.
Yeah.
It seems to me that in the X basis, so when Gx is much larger than J, then it represents the positions. And
well, I mean, I see what you're saying, but I think in this case, we just want some state that has this property that under translations, it picks up the phase that is the same phase that you would pick up, you know, for a state with momentum K. And this is just one state that you can use. You can do different ones also.
And so when you say translationally invariant, you don't mean periodic boundary condition, I suppose.
No, I do. So this
Oh, you do?
discussion that I have here is for periodic boundary conditions, and I also glossed over this. So this, you know, this works when you have a translation invariant system and you have this nice block diagonal structure in a Hamiltonian. So we, because of the constraints of the device, we were not able to run that on the device, but the way we created wave packets was by, So the way we created wave packets was by determining these state preparation circuits with the assumption that we have periodic boundary conditions and then applying them very far away from the boundary so that the boundary effects are very, very small. And and you can quantify how big the boundary effects are by just considering the correlation length essentially. And our wave packets are like 30 sites away from the boundary. So.
Okay, thank you. Very interesting.
So in the beginning, you showed us some other work, some previous work on the scattering. Can you go back to that slide? Yeah.
Or this one?
No, next one. Yeah. What's happening at the bottom right?
At the bottom, very right, is I think is something similar in the U1 theory where they're I think they're scattering two bound states and then they have some probability to produce a different convert one of them to a different kind of particle. So maybe like a heavier hadron or something like that.
So the middle right thing is kind of
I think in the middle they're creating some kind of resonance or some kind of short-lived bound state that decays.
There are also like only the extended boundaries. You're seeing extended strings. Unlike the Ising, where it's individual.
Yeah. That's not the object can stay there.
Any other question for Nikita?
I'll ask one. So when you compare it against the MPS, you mentioned that right now what you're doing is you're basically optimizing it for periodic, but you're putting it in the center away from the boundary. When you're comparing it with the MPS, do you compare the same wave packet constructed in the MPS, or you construct that wave packet out of the true excited states obtained from DMRG?
No, we use the algorithm for both. We use our state prep algorithm for both.
Okay. So do you have any idea of how truly you are capturing the excited states in the open boundary condition MPS by doing this?
Yeah, you can in the open boundary condition MPS. That's a good question. I think we've compared with periodic boundary conditions, like the solution we get from exact diagonalization wave packets.
Yeah.
Compare that to the wave packets produced in our algorithm. Because there's not this block diagonal structure in open boundary conditions, I don't think we've compared directly the quality
one
there.
would expect that since you're putting them at the center, I would expect that if you compute the DMRG spectrum of your open boundary condition MPS, then more or less they should match in energy, and the only differences would be boundary effect. It would be nice to check because
I agree. That's what I would expect also, but we've not done that here.
Any question from Zoom? If not, let's thank Nikita again.